Hey, what's up YouTube? In this video I'm going to do a breakdown of this Niagara particle system I created. It's based on the Boids algorithm. I'll put the Wikipedia link in the video description below in case you want to read more about it. It's an old algorithm invented in the 80s to create emergent behaviors which can be used to mimic how birds and fishes behave in groups. The idea is quite simple actually. You have a bunch of points or particles, each one representing a bird or a fish or whatever, and you encode some basic rules that will drive their individual behavior based on the neighboring particles. The original Boids algorithm had 3 rules. Alignment, which will make a particle tend to move in the same directions and neighboring particles do. Cohesion, which will make a particle tend to move towards the center of mass of nearby particles. And there's separation, which will make a particle tend to move away from nearby particles. Then you can weight those rules, meaning give more importance to, let's say, the alignment or cohesion, and quite magically, if you do this just right, you may see these flock patterns emerge. Particles will then have a tendency to form a huge single swarm, or a few smaller ones, or many even smaller ones, depending on the weights you set for these alignment, cohesion, and separation parameters. It's quite fascinating. So yeah, that's the basic idea and something I try to replicate in Niagara. No, I don't think there's one single right way to implement Boids. It's an idea, right? The algorithm provides guidelines, and disclaimer, what I'm going to show here is definitely my own interpretation and implementation of this algorithm. It's probably not the best, but probably not the worst either. I'd say it does the job quite well. So feel free to take all I'm going to say and show here with a grain of salt and come up with your own unique version. I actually pushed the algorithm a little bit further for my own needs, and so I implemented some extra features. One is a field of view constraint. So normally fishes are able to see pretty much all the way around them, so it doesn't make too much sense to implement this. But I think a fish, when behaving in a flock, doesn't care so much about other fishes that are behind it. They care more about what's ahead and what the flock is doing in front of it, so this field of view constraint is a way to cheaply do this, but more on this later. I also implemented 2 other rules. A fish may not only try to match the flock's movement direction, but also its movement speed and how quickly it can change its direction. So it's a little bit more involved than the basic Boids algorithm. That being said, the good news is that the Boids algorithm in itself isn't that complex, and it's also part of its beauty and the beauty of emergent behaviors. I can only recommend you to take a look at Conway's Game of Life. Veritasium did a mind-blowing video about it. For simple Boids, there's basically just 3 rules we need to program: alignment, cohesion, and separation, and we'll see in a minute that's not so hard to do. And adding even more rules once you have the foundation to code at least one is quite trivial. However, I'd say Boids comes with 2 main difficulties still. One is controllability. It can be quite finicky to fine-tune to have the exact look and behavior you're looking for. And sometimes, if not implemented quite right or not configured quite right, I'd say it can be a bit unstable, like the simulation can end up stuck in some repetitive patterns or something. For instance, at one point I had an issue where fishes were always ending up going round and round in a circle. It was driving me mad. It looked nice, but it was not what I was looking for, and it wasn't just due to the Boids weights, but also how the flock behavior was interlinked with other constraints I had put in my Niagara particle system, like distance and altitude limit. It was messing everything up, but more on that later. So yeah, it can be quite finicky to work with. And then I would argue the second great difficulty that comes with Boids is a technical one. What I mean by that? Well, the idea of this algorithm is that each particle's behavior is based on all other nearby particles, right? And so if you implement this naively in C++ or in your own game engine or whatever, you may end up with a problem which complexity grows squared. Let's assume we have 10 particles. Each single one of them need to check for every other particles, so that'd be around 100 checks. Now let's say you have 100 particles, that's almost 10,000 checks. What about 10,000 particles? That's a lot, but it's not so unreasonable. I can see that happening next gen, right? Well, that'd be almost 100 million checks. So you see it grows at an uncontrollable rate, and that obviously wouldn't work for something that is just meant to be a cool video game FX. So you'd have to come up with a way smarter way to do this, and fortunately Niagara offers us precisely a way to do that, so we don't have to work too hard. We just need to learn how to use it. I'm speaking of the Grid 3D interface. I already had a brief opportunity to speak of that interface in my Niagara State Machine video. Go check it out if you're interested. To summarize though, Niagara allows us to split some part of the world into cells of a given size to create a 3D grid. Each cell is enabled to reference a specific amount of particles. Next, any particle may convert its world position into a grid index to know in which cell it's in, and ask Niagara, hey, I want to know one or multiple attributes, position, velocity, or anything else really, of all particles that are referenced in that same cell, and possibly in the neighboring cells as well. And so we went from each particle having to query all other existing particles to each particle being able to only query the most nearby particles, which is orders of magnitude faster. That's what we may call spatial hashing. I link this great article in the video description below in case you might want to get more familiar with the ID and the Neighbor Grid 3D interface. Now, that interface comes with some constraints. Like I said, for performance concern, we need to limit how many particles we may register in one single cell at a time. So you might actually have for real, let's say 40 particles in a cell, but that cell may only register up to 20 particles, so half of them would be left out, if you will. This may be an issue. A particle might query that cell data, and the cell would be like, hey, I'm aware of those 20 particles, and so if you use that cell data to make a particle avoid nearby particles, it may give you an approximate result because it would only be able to see those 20 particles out of the 40 actually there. But that's fine, we may work around that and accept that some particles will collide and intersect with each other every now and then. It's some kind of visual effects for a video game, right? So it isn't meant to be a scientific simulation, so we can live with some approximations if it means drastically better performance. Plus, if you have 5,000 fishes swimming around with a very nice group behavior, I would argue that players will tend to see the effect as a whole rather than immediately pick up on the tiny details and limitations. The other constraint that comes with this Grid 3D interface is how it needs to be set up, if I may say. You have controls for both its size and amount of cells, right? And the flock behavior you might want to get is kinda tied to this, because let's say you just have one single giant grid cell that can reference all particles, and you have this scenario for some reason. One particle isolated, quite distant from the flock. That particle would get the cell's data, get the information of all nearby particles, and see that there's this flock over there, and naturally, based on the Boids algorithm, it will tend to gravitate towards it. And so you will tend to have one big giant swarm of particles. Now, let's say you have multiple cells, but same scenario. That particle is now only able to query the nearby cells, but there's no particles around here, so it isn't able to see the flock over there. And so the more you add cells, the less a single particle might be able to see the bigger picture and what's going on overall. But again, we do this for performance reasons, and so it's a limitation we have to understand and work with. That's why I'm spending some time explaining all this. I feel like it's important to understand how Grid 3D works if you want to properly tweak this emitter or do your own and make the flock behave exactly like you want to. Again, it's a bit finicky and it's all tied up. The emitter's volume, the amount of particles, the flock behavior you're looking for, the Grid 3D cell size and count, and max amount of particle a cell might register. And so expect having to tweak a lot of settings here and there and experiment a bit until you get the desired result. Anyway, enough of technical talk. I heard you're here for Boids, so let's finally dive in, I guess. The two most important modules happens in the simulation stages down there. Now, they both involve custom HLSL code, so hopefully you're somewhat comfortable with that. We begin with the fill grid module. That's the basic logic used to register particles in each cell. It's nothing too fancy, it's usually always the same logic used to fill the grid. I really recommend you to take a look at the Content Examples project and investigate the Niagara maps. They are filled with examples, including ones that showcase basic usage of the Neighbor Grid 3D interface. There's also the Niagara Fluids plugin that includes some more examples, like this sound emitter, which is great to study the Neighbor Grid 3D interface. Note that the grid interface changed a bit, going from Unreal Engine 4.27 to 5, so there might be some small differences in how things are done, depending on if an example was built for UE 4 or 5. Feel free to reach out to me in the comments below if you have any questions, by the way. Anyway, basically what's going on there? We get the particle's XYZ position, convert it to an XYZ grid cell unit, make sure that cell exists in the grid, and if that cell hasn't yet reached its particle limit, we add our particle's execution index into that cell. Moving on from the field grid, we then have the query grid module, and that's where most of the magic happens. It has this big chunk of code. Now, half of it is common, so don't be too scared. Again, the core logic to make use of the Neighbor Grid 3D interface here is pretty standard. I'd recommend once again studying the examples given by Epic. Anyway, here I'm just initiating all my output variables to 0, and I'll come back to this in a minute. Here I'm initiating the setup to work with the Grid 3D interface, so convert the particle's XYZ position to XYZ grid cell position, then to a grid cell index, then get how many grid cells we have and the maximum amount of particles a single cell may reference. Then we have a first for loop here that goes through the 26 cells neighboring a particle's position, plus the cell that particles is in. Each time we get the cell index we'd like to access, and that's what this list is for. It says begin with the grid cell that is in that box corner here, to eventually end up with the grid cell in the opposite corner there. We make sure that the grid cell exists because we might be, let's say, in that cell, and in that case there's no grid cells here. And then for each of these cells we loop through all particles they may have registered. Now all examples of this given by Epic that I am aware of showcase looping through the maximum particle count, and I am assuming Epic's engineers know what they do, but I was under the impression that this was a bit wasteful. A cell might have no particles, and so I was wondering at first why always loop through that cell's maximum amount of particles if we know it has no particles to begin with. And we know how many particles a cell may contain or reference using that function, and so I tried to loop only for as many particles each cell had registered, expecting way better performance, but it was actually performing way worse, so yeah, I don't know. Maybe I made a mistake, or maybe it has to do with the way GPU thread works, or how for loop behave in GPUs. I don't know, it's way beyond my skills and knowledge. Shout out by the way to both Deathray and Amit Mehar for the help on this. Go give them a follow on Twitter, they both do really awesome stuff using Niagara. Anyway, I was saying, looping through the max amount of particles each cell may register. Okay. Side note, I'm strongly emphasizing how much GPU computation this may require, and I'm strongly suggesting to be kinda humble with the particle count and the max particle count you may set in the Neighbor Grid 3D interface. The higher this number, the more precise that says the Boids algorithm will be, but the cost of this dual for loop can kinda skyrocket. So I'd suggest starting with a somewhat high value based on your particle count. If you have 1000 particles, let's say, and have 5 cells per grid axis, then somewhat like 30 or 40 should be more than enough at first. Then lower it down as much as possible right before the Boids effect you're looking for starts to break down. Usually I can get decent results with values as low as 8 or 10, but that again may depend on the grid cells and grid size, so your mileage may vary. I'm running a 970 GTX by the way, and with 2.5k particles and 12 max particles per cell, this seems to take on average around 0.3 milliseconds to run, so it's not that bad, but I consider this to be quite a GPU intensive Niagara system nonetheless. Be aware of that. Definitely not sure if it's doable at all on mobile for instance. Anyway, moving on. For each particle a cell may contain, get its linear index, and then get the particle index and make sure it's valid and it's not ourself. Then get the position of that particle, compare it with our own position and derive a direction from it. Use this direction to compare with our own movement direction, And since we are aligned to where we are going, it's also the direction we are facing. And that's the check we may use for the field of vision feature. If that is close to 1, that other particle is straight in front of us. If it's close to -1, then it's right behind us. And so if the particle is in our field of vision, get the square distance. That's a little trick. Using a dot product of that same vector will return that vector's squared size. Here we don't really care how close precisely we are to that particle. We only need to check if we are close enough. So instead of using the real distance and comparing that to a distance, we use the squared distance and compare that to the distance squared. It will give the same result, and that allows us to skip the square root needed to compute the real distance, which isn't the cheapest operation at all. And so if this loops, 500,000 times, why not skip it if possible? By the way, I'm really new to HLSL and Neighbor Grid 3D interface as well, to be honest, so hopefully I did all this right. If not, or if you see things that could be improved here and there, please let me know in the comments below. Anyway, then I'm checking if we're close enough to that other particle to fade in our Boids separation effect. If so, based on how distant we are from it, we compute a 0 to 1 linear gradient, which will be 0 if we are right at that separation distance limit, and 1 if we are basically right on top of that other particle. I use that value to fade the position delta and add it to an offset vector that may be used later to push us away from it, like two opposite magnets. And here I use the inverted direction to that other particle to incite us to move away from it. And here I keep track of how many particles we're trying to separate from, so we may then average those direction and offset values once the loop is done. Similar principle here for the cohesion effect. If we are close enough to that other particle for the Boids cohesion effect to kick in, at that other particle's position, so we may then later on average a rough center of mass approximation. Same for alignment. If close enough, get that other particle's movement direction and add it here, so we may average an overall flock movement direction. And same for speed and turn speed really. If close enough, get speed and turn speed of that other particle, add them so we may average those values as well. Once we're done looping through every potential particles that were in all nearby cells, we average all those values. So here, if we may want to separate from at least one nearby particle, average that separation direction and offset. Same for cohesion direction, which is the direction from our own position to the average center of mass. I don't think it's mathematically correct here, but assuming every particle weights the same, I think it's kinda close to the geometric center, I believe, so whatever. And same for direction, speed and turn speed. And then if we specified at least some weights, average the 3 alignment, cohesion, and separation directions. This is not a normalized direction, right? This will be added as is to our own intended direction and then normalized. So the bigger this vector is, the stronger a particle will react according to the nearby particles, if there's any. And that's the basic of the Boids algorithm. You see, it may look intimidating with all this code, but it's not that complicated. It's just a matter of using the Grid 3D interface to average the direction, speed and turn speed of all nearby particles. Now though, that gives us 2 floats and a vector, and we still have to make use of them, and I guess it's precisely the right time to show you how I approach this. It's done in this flock behavior module. Here I have my particle's intended movement direction, so I'm just adding the flock direction based on some weights I may further specify, and then it's normalized. Same for speed and turn speed basically. Here I process that offset value that may help prevent particles from collapsing onto each other. Again, I'm referring to the maximum amount of particle a cell may register, and so our Boids separation direction might not make us precisely deviate from all nearby particles if there's just too many of them in a cell. So I'm using this vector like a magnet force that tries to keep particles at a safety distance from each other. So I'm not changing this particle's movement direction, right? But its position directly. So it may be pushed backward a little bit, but it'd be barely visible if you keep this weight low enough, and it does help a bit to prevent collision, interpenetration and all. But I'm sure this is all still very confusing, so let's actually take a step back and disable pretty much everything in that emitter and start from scratch. So my approach was I first tried to do my best at creating a decent individual behavior. Each particle first tries to apply its own movement, and a movement is made of 4 components: a destination, an intent direction, intent speed, and intent turn speed. Let's begin with the destination. I'm going to turn this back on, and it will complain because I actually set some dependencies for all these modules to ensure that they all are pretty much ordered as they should. I recently made a long tweet about Niagara module dependencies if you want to learn more about it. It's way beyond the scope of this video and it's already long enough, so I'm not going to bother. But basically that module asks for 2 other modules. One is the initiate destination that is here. Turn this back on. In there I'm just making sure the 3 variables used by the destination modules are set to 0, nothing fancy. Then it complains about needing the apply movement module, so turn it back on. In turn, that module complains about needing the generate speed, turn speed and direction modules, so let's turn them back on. And they will all complain that they need their own initiate modules as well. Those initiate modules are nothing fancy, I'm just making sure that the variables used by whatever module are correctly initiated to 0 or to some default values you may specify when that makes sense. So with that, and actually I'm going to spawn one single particle so we may focus on it, we have some pretty basic motion going on. Now, what is the destination all about? To debug this, I'm going to turn on those 2 renderers and this module. This one is a basic sprite renderer, but the position bindings has been overwritten to be the destination position. And that one is a mesh renderer that uses a material to offset a mesh based on those 2 world space locations as sent to the material, location and destination. Here we go. The destination is a point inside the 3D grid. If a particle is near enough its destination, a new destination is generated. Or if a particle has spent enough time going towards the target, it may generate a new destination as well. That time is randomized, so a particle may sometimes chase its destination for a while, and sometimes it may be a bit erratic and choose a couple of new destination points in a short period of time, and go left and right in all kinds of directions. I really wanted to have that unpredictable erratic motion you usually see in fishes. I may also use a bit of noise to shift that destination point around so a particle doesn't just go in a straight line from destination to destination. That destination point is constrained to the grid 3D, and it may also be aware of obstacles using distance fields to try and avoid generating a destination inside an obstacle. If you do turn obstacle on, a particle may also choose to generate a new destination if it gets too close to an obstacle. At first I had another approach, which just involved an intent direction that I was tweaking if a particle was going too far away from the emitter's origin, but it led to all kinds of complications. It allowed me at the time to experiment with a cool concept though. I could force a particle to turn clockwise or counterclockwise if too distant, and so particles could be forced to form a sort of donut shape even without any Boids algorithm on. But yeah, I wasn't happy with that approach and eventually decided to go for that destination point method. It's from that destination point that I derive a direction in the generate direction module. It's super simple. And actually both generate turn speed and speed are even simpler. It just forwards an input value to those 2 values. So we have a basic movement. We have a destination from which we derive a direction. We have a speed that will determine how fast we'll move in that direction, and a turn speed which will dictate how fast we change from our current movement direction to the new direction. Apply movement down there let me ensure a maximum speed limit, and let me specify how fast a particle may accelerate to reach its intended speed if its current speed is below that, and how fast it may decelerate for the other way around. Or you could use a simpler float interpolation. It's a bit cheaper and a bit more fluid, so you might want this or not. Feel free to try this out. We also interpolate our current turn speed to reach that new turn speed in case it changes to smooth out the behavior. The turn speed will dictate how quickly we may move towards a new direction, and we may derive an angular acceleration based on our current movement direction and the new one we computed. That's sent to the shader to drive how much a fish mesh bends. More on that later. A linear acceleration is also computed in here based on our current speed and the new speed for this frame and the delta time, pretty standard. Okay, cool, now let's take a step further and modify our speed with a curve. That complains about needing its initiate module, so let's turn it back on. Here we may set how long in seconds that curve should be. By default it's 30 seconds. So that curve here describes how much the intent speed of a particle changes in that amount of time. When a particle is spawned, its current time is randomized, so not all particles are in sync on the curve. One might start here, one other might start there, and so on. And that curve describes how much in percent our intent speed is tweaked. So around here it's 20% faster, here 75% slower. We may further increase or reduce this with that alpha value. So here the curve effect is halved because I felt it was a bit too strong. Cool, so that changes our movement speed a bit over time and introduce some variation. Let's add burst. To do this we'll enable all the necessary modules. Every x seconds a burst will be generated and will last x seconds. And during that time we increase the intent speed by that much. So we can tweak the delay, duration, multipliers and so on. Again, I really was looking for those erratic sudden bursts of movement you tend to see in fishes. Not all of them obviously do that, they can be chill on coast, but I'd say most of the time it's pretty erratic, so that's what I was trying to do. You can turn this off anyway if you don't like it. Okay, cool, what else? Let's check the altitude limit. That's pretty straightforward. You may say, hey, particles may not go above or below those altitude limits. So if it's in local space, that'd be 400 units above the emitter's origin. If in world space, that'd be 400 units in the in-world space. And simulation is one or the other, depending on the emitter's setting here. So that may be used to clamp the particle's position, but that can be a bit ugly, because a particle could move upward and then suddenly hit that invisible wall and keep trying to move in that direction. So you may also use that altitude limit to smoothly constrain the movement direction. And same for destination. A new destination might be clamped to those altitude limits to ensure that no particles is incited to move towards an unreachable target. A quick side note though, depending on where you set those limits, you might end up wasting some of the 3D grid cells we use for the flock behavior, so try to work around that. Maybe set a lower height for the grid 3D and lower grid count in Z to account for those altitude limits if you do set some. What else? Okay, let's talk about generate flow. It will complain about needing both the initiate flow and flow apply modules. No big deal. The idea here is really simple. We have some flow vector that is increased by sampling some low frequency 3D noise and faded out over time, and we use that vector to offset the particle's position. This is precisely made so this flow motion isn't registered as a velocity. It's added the same way though, meaning at delta movement times delta time, but it's directly fed into the particle's position. That way it doesn't alter the velocity in any way, and I wanted that because our particle mesh renderer aligns the particles towards their velocity. And so we might then get a particle moving backward if the flow force is strong enough, but still oriented forward, and it would look like a fish is fighting and swimming against the current, which is exactly what I wanted. That flow may also be constrained by the min and max altitude limits, so no particles are pushed by the flow higher or lower than they are allowed to. I may also limit this flow by some other value. Here I don't want particles to be pushed way out of the grid 3D. A little bit is fine, but definitely not too much. So I'm using this distance weight that the flock module outputs to control that, but more on that in a minute. Great, we are making some good progress. We are pretty much there. Let's talk about obstacles. There's a first obstacle constraint here, so when particles are spawned in this box, they might be safely placed outside obstacles as much as possible. It's quite straightforward. Get the particle's position in world space, sample the nearest surface, and offset that particle's position from that surface if it's too close to it or inside it, and transform that position back to simulation space. And actually that same constraint is used down there to ensure that particles do not go through obstacles. So when the movement, flow, and everything is applied, I do this to ensure that all this movement hasn't led me inside an obstacle. Before the movement is applied, but after it's been generated though, I may alter both the intended direction, speed and turn speed, based on how close to an obstacle I am and how much my intended direction is making me go towards that obstacle. So I may be close to an obstacle, but that's fine as long as I'm moving at most perpendicular to that surface or away from it. Else, the intended direction is modified, and I may be given some extra speed and turn speed to move away from that nearby obstacle. The flow can also be constrained by obstacles, because again, flow is applied as a position offset, so we should try our best not to push particles inside obstacles, despite our constraint down there, ensuring this as a very last safety precaution. So I already sampled the nearest surface in this obstacle module, right? So I might just keep resampling it again in this module, and so I may use the values this obstacle module outputs. Then I check if the flow force is pushing me towards an obstacle, and depending on how close I am to that obstacle, kill the flow. So even if I'm very close to an obstacle, if the flow is pushing me away from it, it's fine. The other way around, though, not so much. Okay, we are almost there. There's this simple point avoidance behavior you might want to add, so particles may flee from a given predator or your character, whatever. You may set that user expose vector in blueprints to send your character's location, and then this module will modify our intended direction, speed and turn speed, just like the obstacle avoidance behavior module does. So once we have that intended move direction, however modified if it had to be by that obstacle and point avoidance behavior modules, we may choose to limit how much in Z a particle may move, because fishes don't usually swim straight up or down, and more importantly, if a particle has no movement in X or Y, and thus no planar velocity, Niagara will not know in which direction to orient the mesh, so this here simply clumps the movement direction to a max Z value, both in positive and negative directions. Note, this may actually prevent a particle from moving away from an obstacle like it intended to, but it's fine. That's also why I put this safety obstacle constraint down there, right? Once we have all that, we might start to fade in the Boids algorithm. So turn on the flock behavior and initiate flock modules, which again, this one is just here to ensure that all variables used by the flock behavior module are all properly initiated to 0, and flock weight, which is just a helper module to output a value that will control how much flock behavior to fade in. It starts with a weight of 1 and will decrease the more a particle might need to behave on its own. So if it needs to flee from an obstacle or a given point in space like a predator or your character, it should do this straight away on its own and not wait for the flock to react, right? So the more we avoid an obstacle, the less will fade in the flock behavior, same for point avoidance, and also if we are getting close to the grid 3D borders. And actually this module outputs the grid border gradient that I can use in that flow drag constraint down there, so the flow is killed when a particle is nearing the 3D grid borders. That allows me to skip computing that 3D box gradient twice. So once I have that global flock weight computed and set here in the flock behavior module, I may choose how much of this individual flock behavior, direction, speed, turn speed, and also that offset, which is the opposite magnet force I talked about a while ago, are influenced by that global weight. I would definitely assume that you do for the direction, speed and turn speed, but maybe not so much the offset one. You probably might want to have particles repelled by each other despite them avoiding an obstacle or something, right? But anyway, then I may further tweak each individual weight for those parameters. Let's say direction. The higher this value, the more this particle is going to match the flock's direction. Remember that the overall flock Boids direction, right? So it's the one computed down there based on those 3 individual weights. So you definitely might want to tweak these, and the distance threshold as well, and how much overall Boids direction you end up adding to that particle. So my approach was 1. Try to create interesting individual behavior first, and then have that be enhanced by the Boids algorithm. So it kinda acts as a post-process effect, right? It's added pretty much as the very last step, once everything is computed and just before movement is applied. Oh, almost forgot those two. The animation module is quite straightforward. First, interpolate over time the acceleration, because it may change quite abruptly, so I wanted to smooth it out, and same for angular acceleration. And then I increment an overall animation time based on the acceleration and speed, and that's a value used in the material to drive the swim animation. So a fish may coast and swim at least a little bit based on its speed, but also swim super fast when it accelerates. And then these 4 values are sent to the material using a dynamic material parameter. Speaking of materials, there's one cool thing I have to mention though. I really wanted to have those fish curl when they turn, because if not they feel super rigid, right? It looks like they are made out of wood and it doesn't look too believable. So I tried to tweak the mesh using world position offsets to have that tail whip action when they turn. At first I tried to do this with a simple rotate node and some mask along the length, but I couldn't get this to work. I had some extreme distortions, and I didn't want to bake poses or vertex animation into texture users like I experimented with when I was fooling around with my shark. And one day I was using Blender and its cool bend modifier, and I thought it was exactly what I wanted. So I had a look at its source code and eventually managed to port it to Unreal Engine using this custom node I wrote. Huge shout out to Daniel for suggesting me a way to fix the normal. He's an engineer working at Epic. Go give him a follow on Twitter and YouTube. And also Amit Mehar once more for suggesting me to use the preskin location node, which I thought was for skeletal meshes for some reason, but turns out it works for static meshes as well and returns the local vertex position so you can skip a transform. That's neat. Anyway, this bend amount is driven by how much the particles turn at a given time. That's the angular acceleration I computed in Niagara based on how much a particle changes direction over time. Back to Niagara, last module is the LODs. That's really straightforward. I have these 4 mesh renderers down there, each having a unique visibility tag. And then in there I get the camera's position in world space, compare it to the particle's position in world space as well, and so based on the distance between the two and those LOD distances, I set the correct visibility tag. So 3 here is for the most distant renderer that uses the most simple mesh. And that's it, I think. Did I forget something? Probably. Not sure. This is a big chunky emitter. So yeah, anyway, hopefully you could make some sense of all of this. Feel free to use the comment section below to ask me questions if you have any. Alright, files are available as a tier 2 reward on my Patreon. It's been crazy this month. It grew so much and I'm very grateful for all your support. Let's end this video with a chill time-lapse of me modeling, sculpting and texturing that little fish. Thank you for your time and support. I'll see you in the next video. Take care of yourself. Bye bye!